everybody. Welcome to the National Science Week 4th event of the Stars in the Yarra Ranges program, brought to you by Mount Bennett Observatory in conjunction with CAASTRO, the ARC Centre of Excellence for All Sky Astrophysics. Tonight we've got two speakers for you and they'll be doing rolling talks, relatively short talks so that you can get in and out and do various other things. The first speaker is Dr. Ewan Barr, and he's at Swinburne University and also affiliated with CAASTRO. And he's going to be talking about the SKA, which is the Square Kilometre Array Telescope. Please make him welcome.
Right, Mike, good? Excellent. So I'm from Swinburne, and for a living I work on the Square Kilometre Array, which doesn't actually exist yet, so it's quite hard to work on it physically, but I'm working on designing the Square Kilometre Array. And in this talk, I'll hopefully give you an idea of why the radio astronomy community is spending so much effort on building this fantastic instrument so that we can probe the universe and discover things which we've never seen before. So, as radio astronomers, we ask some pretty big questions on a daily basis. Some of these questions are something along the lines of, how did the universe form? How did the universe come to be as we see it today? Why are there X number of some type of galaxy and Y number of another type of galaxy? These are big, important questions in understanding how the universe looks like it does today. We also ask questions like, how does the universe work? You know, what are the rules which define how the universe operates? And there's some more esoteric type questions that we're starting to ask kind of in more recent years anyway. Things like, where does life come from? What are the building blocks for life? How do planets form and how do those planets generate life? And that naturally leads on to, are we alone in the universe? Is there other intelligent life out there? And can we find it? Can we detect it? So, to do these things, you need to have a telescope. You know, theory can only get you so far. After a while, you need to have an instrument which lets you look into the deepest corners of the universe to find the evidence and the proof of your theories. And for us, that telescope is going to be the Square Kilometre Array. Now, you see this video here? It's a flyover of an artist's impression of the Square Kilometre Array. And the first thing you'll notice is these don't look like your traditional telescope that you would put to your eye and look to the sky. And that's because these are radio telescopes. They operate just like a satellite dish would do on your house. They receive radio signals from the sky, convert them into a signal, and then we record that signal, and it allows us to look at the sky in radio light. Now, the SK itself is composed of many, many, many of these little dishes. So each of these dishes you're looking at here is about 15 meters across. And there is well over 2,000 of them. It's also composed of these smaller type dishes. These aren't really dishes, these are what we call dipoles. These are just simple little structures that observe almost the entire sky at the same time and allow you to do fantastic, what we call wide field imaging, looking at the whole sky at the same time. So there's going to be, in the SKA, somewhere in the region of 500,000 of those. And altogether, this telescope is going to give us the ability to probe deeper into the universe than we have ever looked before. With higher sensitivity, we'll be able to look at it faster than we've ever done before as well, be able to look at the entire sky in a matter of days. It's really going to be a fantastic instrument. And to give you an idea of why it's going to be a fantastic instrument, you have to consider what makes a radio telescope great. And you can kind of quantify it in terms of size. So, if you have a very big radio telescope, it's great because suddenly you have a huge amount of sensitivity. You can collect a lot of light, a lot of radio light in a large radio telescope. And it gives you very high resolution. That means you can see things that are very small. But that's a problem because to see something that's very small, you need to look at very many places to cover a large area. So what you can do instead is you can say, well, why not actually make a very big telescope out of a lot of very little telescopes? And this gives you something called field of view. And field of view basically says the smaller your telescope gets, the more of the sky it can see. Now, if you have very many small telescopes, you can look at a very large patch of sky, but with the same sensitivity that you would get from one single very large telescope. And the way this works is through the process of interferometry. So up here, this red, purple, and green kind of poles, these, for the purposes of this demonstration, are antennas of a radio telescope. And if you have some radio light coming in from the universe, and it's coming in and it's hitting your telescope, it doesn't quite hit every single telescope at the same time, every single one of these antennas at the same time. There's a slight delay. So if you look at it like this, you have an incoming signal, and it hits your first one, and you get a little spike. It then goes on and it hits your second one, and you get another little spike. And it hits your third one, and you get another little spike. Now, if you're clever, you can adjust in software or hardware for the delays between the different times when the signal hits each antenna, and you can reconstruct that all into a single very bright signal. And that allows you to operate with very many small telescopes as one single large telescope. So, you see how it works, basically, and it's going to be very large, but what's it actually going to tell us? What's it going to give us? And I'm going to give you two kind of fairly specific examples here of what the SK is going to give us. So, there are four fundamental forces that govern the universe. Does anyone know what they are?
Gravity, electrostatic, strong, and weak.
Fantastic. The man got it in one. So, for those of you that don't know, there are four fundamental forces. There's weak, strong, electromagnetism, and gravity. And they govern everything in the universe. Now, one of these is an odd one out. Does anyone know which one is the odd one out? So I heard several people say it there. Gravity. And gravity is odd for a couple of reasons, but the main one is gravity is billions of billions of billions of times weaker than the other three, right? And the other three are all described by quantum mechanics. Gravity is not. Gravity is something else entirely, or not entirely, rather. Should we say that we haven't found the link yet? And so we have to ask ourselves, what is gravity? Do we understand gravity? It seems so simple. All of you are sitting in chairs right now. You're not floating up to the ceiling. Do we understand gravity? Well, someone who thought he understood gravity was Sir Isaac Newton. And Newton said, basically, gravity, if you have a thing of mass 1, a thing of mass 2, and they're some distance apart, the force of gravity between them is the mass of one times the mass of the other divided by the square of the distance between them. So he said gravity is a force. He said it scales with mass and distance. And what he did was he said, basically, this is my theory of gravity, my law of universal gravitation. Now, turns out that he'd actually come across a specialized case of gravity, what we call a weak field limit. So this is where you don't have a huge amount of mass in a very small area. And actually, when you do have a really extreme system, you need to change. You can't follow Newtonian gravity anymore. And this is where Einstein came along. And Einstein said, actually, gravity isn't a force. It's the curvature of the fabric of space. It's the curvature of space-time. And he said, instead of scaling with the mass and distance, it scales with energy and momentum. And this changed everything. And so this theory, which generally is called general relativity, generally referred to as GR, this allows us to make predictions about gravity in the most extreme environments in the universe. And actually, this is really interesting because we want to test gravity. We want to understand gravity, right? So we have to go to an extreme environment. And one of those extreme environments are binary pulsar systems. Now, a pulsar is basically what you get when a quite massive star dies. It gets to the end of its life, it explodes, and the core of that star collapses down very rapidly. And all the electrons and protons in that core get squeezed into each other to form neutrons. And you end up with a sphere about 10 kilometers across which contains the same mass as about 1.5 times of our sun. So this is insanely dense, right? This is incredibly dense. This is nuclear density matter. And it spins up to 700 times a second, right? You take any household blender, it is slower than that. These things are unbelievably extreme. Even the surfaces are moving at significant fractions of the speed of light. What's great about pulsars is you can see these bright, flashy beams coming off. Well, this is radio emission that comes from above the magnetic poles of these pulsars. And as it sweeps across the sky, it's like a big lighthouse. And you can look to the sky in radio light, and you will see flashes like the flashes of a lighthouse. And when they're in a binary system like this, you can do some fantastic science by looking at how the rates of the flashes change. And so you end up being able to probe gravity in one of the most extreme regions of the universe. And we've been doing this for years. And don't worry too much about these specific plots, but for any of the astute among you, this on the left-hand side is a very, very famous plot, which actually is part of a paper which went on to win, well, the people that came up with this plot went on to win the Nobel Prize for their work in this field. But basically what they have here is a prediction of general relativity is this black line running through the plot. And what it's saying is this binary pulsar system where you have these two very fast spinning stars orbiting each other, it's expected to get smaller. They're expected to get closer to each other with time. And it's exactly predicted by general relativity. The black points are the measurements over 25 years, more than that, 30 years. This is not a fit to a line. This is how well general relativity predicted the behavior of this star system over 30 years. This is incredible, and like I said, it went on, and the authors of this, the people that discovered this, went on to win the Nobel Prize. So that's pulsars and gravity. The other big question that we're looking to kind of get on top of with the SKA is the formation of the universe, and how the universe came to be as we see it today. So most of you will have heard of the Big Bang, right? So what happened after the Big Bang? That's what we want to know. So you have the Big Bang, and then you have this thing called inflation. It's all a bit crazy. And then you kind of keep on going through, and there's a point. So everything on the left of about here, the universe is just neutral hydrogen. It's just like a big kind of sea of neutral hydrogen with nothing really interesting going on. And at about that point, we have something called the epoch of reionization, or EOR. And what happens is the first stars and galaxies start to form. So little density variations in this neutral hydrogen mean that it starts collapsing under its own gravity. And stars start to form. And those stars start to be attracted to each other, and galaxies start to form. And this is really interesting for us because it tells us a lot about how the universe started to be the way we see it today. So what happens is when these stars start to form, when they ignite and you get fusion, they blow a little bubble in space, basically. So they blow away all of this neutral hydrogen and form all these bubbles. And you can see them here. You have a few bubbles at the beginning, and as you move on in time, so this is time going from left to right, these bubbles start to expand. And eventually these bubbles meet, and the universe becomes what we call totally ionized. All of your neutral hydrogen becomes ionized, and suddenly we move into the region of what we call the modern universe, where we have stars and galaxies as we see them today, or in early forms of as we see them today. So that's the big questions, two of the big main questions for the SKA is start of the universe and gravity. And I'll just finish up by saying the SKA is an enormous project. It's huge. It spans 2 continents. Half of it's going to be in South Africa. The other half's going to be here in Western Australia. Well, not here specifically, but in Western Australia. It's going to require infrastructure on those 2 continents. It's going to require a lot of computing power. It's going to require roughly 100 million of these, which I think you'll agree is a fair amount. It generates a lot of data. You know, you have a lot of dishes looking at the sky all at the same time, and they all sample very quickly, so they're very rapidly acquiring data. And I think it's the only way I could put this into a number which kind of means something to people is to say it's going to generate about 125,000 HD movies a second, right? For any computing geeks in the room, that's 10 petabits a second of data. There is literally no other project on Earth which is even coming close to these kind of data rates. And this is a problem because how do we deal with this? What do we do with it? What we need is we need a new generation of astronomers. I'm looking at all the youngsters in the room, right? We need what we call a big data astronomer, someone who comes into astronomy and they understand computing, they understand data, and they can come into a project like this and they can really make a difference. And that's a big thing for us at the moment, is finding these kind of hybrid astronomers who are going to be able to deal with all of the data produced by the SKA. Yeah, and just to finish up, in the end, it's going to cost quite a bit as well, which I'm sure someone was probably going to ask at some point, so I thought I'd put it on a slide. So the projected cost at the moment for the first stages of the SKA is about 650 million euros, and we expect that to go up to about 1 to 2 billion when it's finished, and that's going to be in about 2022 probably. So I'll leave it there. Say the SKA is going to be fantastic, and if you have kids who are interested in astronomy, now's the time to get them into radio astronomy, right? Thank you.
We can take a few questions if you've got a good one, and you might even win yourself a ball from the box.
How long will it take? How long will it take to make the SKA?
So, a long time is pretty much the answer to your question. So the design phase of the SKA, which is what we're currently in, will be finished by about 2016. After that, there is a tendering process, and we put it out to companies to see who wants to start building different parts of it. And that's 2017 onwards. And the first kind of stage of the SKA, it's going to be built in 2 stages. There's a phase 1 and a phase 2 build. The phase 1 build is expected to be finished by about 2018 to 2020. The phase 2 starts in 2022. All right. So, this is something where I'm really meaning this. If kids in the audience are going to be the ones who are coming through at just the right time to hit it as it becomes a big thing, in 2025 and so on. You should get a ball for that, absolutely.
What's your computing bus? There's nothing around that can handle terabits per second at the moment.
Oh, there is. Just you have to think that it's aggregate, right? So it's gigabits on one line, gigabits on another line, and if you have enough lines,
so you got to aggregate them all.
You have to have it's all parallel, right? You have to have everything split up. The problem in scale comes here not from a single instrument producing an infeasible amount of data. It's from thousands of instruments.
You limit the physical write.
Well, you mean you're not writing to a single disk, right?
Yeah, but it still limits the signal.
You actually never write into a disk.
So what are you writing to?
So when I say it's creating 10 petabits per second, we actually feed that all into FPGAs and ASICs, right? So if you're familiar, this is like dedicated hardware systems. That all goes through, and actually you can compress your data massively.
You still got a limitation.
You don't actually. You just need more computers. It's actually the truth, right?
You need more power and everything else.
It's a very paralysable problem.
The limitation thing.
Yeah.
So
solar energy. It's Western Australia.
That's a serious problem. That's one for another time. But yeah, solar energy, a big deal for us. Yes. Question. Oh, that's an interesting question. It's kind of a difficult one to answer. So when you look at light comes into your eye, right? And light is just one part of this, what we call a big spectrum, right? So you get red light and you get blue light. There's more types of light beyond that, and there's more types of light below. You just can't see them, right? So there's all this stuff in this room right now. There's all this stuff you just can't see, right? And you can build special telescopes like this one that lets you see that stuff that your eyes can't. So it's a different type of telescope. We're looking at a type of light that just, unfortunately, your eyes can't see.
She gets a ball.
She definitely gets a ball for that. Hey.
Wow.
Politics.
What was the question?
Why was it built on 2 continents? It's an exceptionally good question. Can I just give you the ball? Just to answer that question properly, in brief, it's built on 2 continents purely because of politics. Funding streams from different governments mean that it was a decision taken that it was better to have it in South Africa and Australia rather than just one or the other.
What's the distribution of the different types of antennas over the 2 continents? Are they going to be fairly homogeneous?
No, absolutely not. So they're going to have. So SKA comes in 3 frequency, or it comes in 3 antenna types. There's what we call survey, which are they're like 50 dishes, and they're fitted with a phased array feed system at the top, which allows you to get very wide field of view. They and the low frequency antennas, the dipoles, the very small ones, they're all situated in Australia. So they're all going to be out in Bullardy in Western Australia, in the Murchison Widefield Array kind of area. And all of the mid-frequency stuff, which is this kind of, they also look like the survey dishes at the moment, but instead of having a path, they have quite a wide bandwidth, and they go from about 650 megahertz to 10 gigahertz. They are all in South Africa.
So we're not going to have the resolution that we could have if there was a more even distribution?
No, I mean, you're still going to have the same length of baseline. But if you mean, why isn't there part of the mid-frequency in South Africa and part of it in Australia, and you could use both?
Exactly. I think the photometry is going to be...
Well, I get, actually, there's an argument to be made for that, and there may be facility built in where there's part of a little bit in each place so that you can use it like that. Yeah.
So, like, when was it decided that they'd start the SKA?
In about 1990. Actually, it might even be before that. It's been a long, long time. So some guys came up with it, and it was just an idea, and they thought, there's no way we can do this. It's too big. It's too crazy, right? There's too many dishes. You need too many computers. And then time went on, and suddenly we found all of our computers were getting better. You look at your phone, right? Your phone is as powerful as a computer was 20 years ago. In fact, 10 years ago, right? So suddenly, we've got all this power, all this computing power that we can use. And things like this then become possible. They stop being fantasy and they start becoming reality.
Why is it only built in the 70s?
Mainly because you can see the galaxy in the southern hemisphere, and also in the southern hemisphere it's easier to find space for things like this. And there's politics involved as well. I mean, there is no large radio facility in the southern hemisphere, barring the Parkes Radio Telescope, and ATCA as well, of course, and any of the other Australian observatories. There's some smaller facilities in South Africa, but really in the north there's loads. There's the Greenbank Radio Telescope, you know, there's lots of large arrays. There's Chinese arrays, there's the Urumqi Telescope, there's the Effelsberg Telescope. These are all 100-meter class instruments. In the south, you see the galaxy more of the time, of course. I mean, the Australian sky is phenomenally beautiful, right? So you have the opportunity to see the galaxy more of the time, and for galactic science, that makes a huge difference.
I think one more question. And yeah, whoever asked that should get a ball. Who wasn't it? Oh, no. Share your science one.
How many stars is there in the sky? There's 1 followed by 24 zeros. So there's a lot of stars in the galaxy, right? We have this galaxy, and it's got what we call 1 trillion stars, right? And for every star in our galaxy, there's another galaxy. So there's 1 trillion galaxies, right? So 10 to the power of 24. There you go.
We should
Definitely
stop there.
deserves a ball.
In the future, we'd like to come down and just ask you questions privately. That would be fine. I'd like you to thank Dr. Ewan Barr for that really interesting talk.